Hi. In this video, we are going to analyze one of the papers that we published recently for detecting AI versus human generated text. So the paper is already published on arXiv. It's you can find it if you just search HULLMI. It's short form for human versus LLM identification with explainability. So and of course, hats off to Prathamesh, Sahil, and everyone else, Raj, Rajat, for putting this work together. But this video is a short review of this paper to explain to you in very simple terms what exactly was this paper about. And this paper is also now accepted to NeurIPS workshop, which is happening in Vancouver, Canada. So we visit a lot of schools for giving our solutions and products. And recently, in the last few months, whenever we visited schools, teachers were asking us, is there some solution for you to help us detect if a student submits an assignment, whether it was written by the student themselves or AI? A different version of this problem existed always, whether the assignment is written by the student or the parent. But in this age, the problem has become whether it's something is AI written or student written. So we were thinking of developing a product for this. And while building that, we realized that this is not at all a simple problem statement. Although certain products like Quillbot, AI detector, etc., exists out there, there was really a good scope for a full-blown research problem. And that research problem was framed as identifying human versus AI generated text. So we decided to work on this paper. And what we did was very interesting. We used several different advanced NLP models, natural language processing models, as well as some traditional machine learning models. I'll come to that in a moment. But you should not think that this AI versus human generated text detection is only important for education. Of course, it's important in education sector. Academic integrity is a big thing. If we are always taking the help of large language models for writing, then we are never thinking deeply. We are not trying to articulate our thoughts, and it's a big part of what it means to be human. So of course it's important in education, but also in news or journalism. Like if you are reading a certain piece of news, can you really trust that? Actually, whenever I read some news articles on news websites, I often feel like, am I reading something that was generated by ChatGPT, or am I reading something that was actually written by someone working at this news company? So this is always like a nagging thought for me, and it often makes me less motivated to read certain articles. In cybersecurity, there has even evolved a term where LLMs can be called as weapons of mass deception, similar to weapons of mass destruction. And if LLMs become so convincing that it can generate really, really human-like text, then imagine in Facebook, there are so many fake profiles who can make narratives or who can start discourses which are very, detrimental to the entire democratic process itself. It can sway elections, and many, many things can happen. So it's also equally important in politics. Now, the question is, you may have come across certain paragraphs where you obviously felt like, hey, this feels like ChatGPT written. And I also personally have a radar for this. So to give an example, let's say you read paragraphs like, instead of writing "we have," if you see too much usages of this, or let's say instead of "I am," there is too much usage of this. I'm not saying that people do not use this. Of course, people use this, but ChatGPT often almost always use this. So whenever I see this, I can kind of say that it's ChatGPT written, and then if you copy paste that in Quillbot AI detector, it can also show that, oh, this was 95% written by AI. So, but that being said, there are many different LLMs out there. Even ChatGPT can be asked explicitly to generate text in different formats. So it's almost impossible to say with certainty what is AI generated and what is human generated. Even, kids who are submitting the assignment, they could give a prompt saying, write this article, write this essay like a fifth grader. They can do that. And then ChatGPT can create essays which read like how a fifth grader would write. So of course, this is a problem. And then we thought, okay, we could train some already existing natural language processing or machine learning models, and there is a lot of data available. So that was the first thought that came to our mind, and we tried to do that. But before going into that, I also want to talk about what people have been trying to do. So there are, of course, advanced natural language processing models like Roberta Sentinel, T5 Sentinel, etc. Then there are other approaches which are mostly stylometric based. So what this means is you rely on the linguistic styles. But I would say stylometric approaches are very weak, especially today, because these large language models can pretty much write in any style that you ask them to write. So it's impossible. Like if somebody is really, really bad at prompting, maybe yes, stylometric approaches can, like similar to the example that I gave you, like we have, instead of we have, writing it as we have, something like that. So those are things that you can capture, but it's also because of bad prompting. There are also hybrid approaches which look at both. It looks at stylometric things, plus you also implement traditional machine learning or advanced machine learning models. What was really lacking in the work that was done today was, like in the current approach until we published our paper, was do traditional machine learning models like XGBoost or naive Bayesian or random forest, do these models actually work for detecting AI versus human text, or only advanced NLP models can be even thought about attempting? So that was one question that we wanted to answer. The other question was, how much can we interpret what the model is actually seeing? So similar to what I said, is the model also seeing like phrases like we have or I am, instead of writing something as I am? You can also write it as sorry. You can also write it as like this, or we are can be written as like this. So we just wanted to see if we can somehow interpret the model. Is the model also looking at these kinds of phrases, or is it something else? So that was another question. So basically, our research methodology involved a few different steps. The very first one was dataset generation, because we were pretty sure that if the dataset quality is not very good, the results will not at all be good. So I also experienced this, like while trying some of the initial models, we were getting actually 100% accuracy. And the reason for that was that there were multiple reasons. So in one of the attempts, we had a highly like a biased data set. So it had 10% AI generated and 90% human generated. So let's say the model is really good at identifying human generated text. This is human, but really bad at identifying AI generated text. Then model will 100% detect all of this, but among this 10%, maybe the model is getting it right only half of the times. So ultimately, if you look at the accuracy will be 95%. But it's actually a very bad model because it cannot detect AI written text at all. So there were these are basics of even training any ML models, but these are some issues that people will inevitably come across if you download data sets from internet like Hugging Face or Kaggle without properly looking at what exactly the data consists of. Another issue that we faced was like this. So we were looking at data set which consisted of articles which are scientific abstracts. So these were abstracts from paper. And the interesting thing was, I mean, all of these abstracts were human written because it was well before 2019 or something. And there was no chance that it was AI written. This day, perhaps there are authors who publish articles which are written by AI. But the interesting thing about this abstracts was it had a lot of special characters, units, etc. So let's say alpha, beta, these kinds of Greek letters are there, or like meter per second square, or watt per centimeter square. If these kinds of units are present, then let's say now human generated text is all about this. This is human. Sorry about my pen. So if human generated text is primarily consisting of this, and if AI generated text is primarily consisting of, let's say, something related to English literature with minimum amount of such special characters, then automatically an AI model will learn to detect whenever these characters are these special characters, symbols or Greek letters or units are present, it will be denoted as human written. All other will be denoted as AI written. But then, if in an actual testing, let's say you ask ChatGPT to write an abstract, which actually consists of some of these units and symbols, then it is in reality it is AI generated, but it may also be detected as human generated. So there were problems like this. Then there were issues like sometimes if you get download data from internet, it will have these special characters like slash and slash next line, or maybe some other slash slash. So these special characters might be present in the text. And then if this is present in a way that it's only present in human generated and not present in AI generated, then that also kind of biases the model. Then the model is not good, because then the model is not truly learning the aspects of the AI written versus human generated text. It's just recognizing that, oh, only in human generated text these slash n or slash characters are present. In AI generated it is not present. So this is also not good. So there were several few different considerations like this that we had to make. So excuse me. So dataset generation itself was a big deal. I'll come to that in a moment. A little bit more details are there to be shared with you. Then, of course, there is the normal data pre-processing step. For example, removing these slash n characters, etc. Then defining different models. So we were using few traditional models as well as advanced models like T5 Roberta, T5 Sentinel, Roberta Sentinel, etc. And then tuning the hyperparameters for each of these models, then getting results. And finally, most importantly, we also implemented a technique called LIME. LIME means local interpretable model agnostic explanations. So it is an explainable AI technique where we can highlight the words that are, so let's say you give a paragraph to the model to predict whether this paragraph was AI written or human written. And the model will predict, 98% this is AI written. Then using LIME, we can also highlight the words or phrases within that paragraph which contributed maximum towards making that paragraph AI written or human written according to the model. So that is why we use LIME, and the results are interesting there as well. So firstly, in the dataset generation, initially what we did was, okay, there are so many good AI versus human written data available on Hugging Face, Kaggle, and other places on internet. So basically, we found this Open GPT text data. It's analogous to Open Web text data. So this Open Web text data is data which are primarily human generated well before 2019. So it's like the web text data corpus. So similarly, the authors of a particular journal, they curated Open GPT text dataset, which was the AI generated version of AI analog of Open Web Text, and it was generated using GPT 3.5 Turbo. So we had Open GPT text data and Open Web text data. So this was human written and this was AI written. Then what we did was there was a data pre-processing step where firstly, as I mentioned, like these characters has to be removed. So for example, new line characters so initially duplicate data and new line characters were removed from the data set. By duplicate data, what we mean is if there are, let's say, 29,000 data sets in a particular AI generated like OpenGPT text data, we have no idea if there are repeating rows or not. And this was another problem that we encountered in many data sets. Repeating data was there. So if the data is in a table format, 2 rows of the table will be exactly the same. And this was there for many data sets. And then the issue is if you do random train versus test splitting, sometimes the same data that is present in training data will also be present in test data. And this was also giving us a false sense of good accuracy. So we had to remove duplicate data. We had to remove these new line characters. Then we implemented tokenizer. So basically text data has to be tokenized. Tokenization, you can, in simplest terms or oversimplified terms, you can imagine it to be sentences being split into words, but that's not exactly how it works. Then sometimes in some data sets, there were out of vocabulary words, and we replaced that with special token like this. And then finally, after this much data pre-processing, we split the data into 80% training and 20% testing. So this is what we did. And there is one interesting thing which I want to mention. So in the tokenizer, so often we denote some words. There is the vectorization process, right? So for example, let's say there are two axes, and a word like cat, we can represent words as numbers, and numbers essentially vectors. So words like maybe cat might belong here, then dog might belong here, then whereas let's say apple might belong here, and orange might belong here. So basically, this vectorization process separates the words and helps you cluster them in such a way that words that have some sort of similar meaning are close to each other along certain axes. So apple and orange being fruits along certain axes, it will not be a two-dimensional vector. It will be multi-dimensional vector like a tensor. But along certain dimensions, these words might remain close to each other. Here, because dog and cat they may often appear in sentences together, but dog and apple probably won't appear in sentences together. So automatically these vectorizers can learn this property. But one more additional thing. So there was like a bag of words that we created. So bag of words mean all the collection of words, different words that are present in the in your entire corpus of data. And some words will be repeating. So basically, we need to know the frequency of words. Now you will understand that this has an issue, because filler words like, or rather more than filler words like was, is, the, of, if, all these words will appear in almost all paragraphs, right? So there is something called as term frequency and inverse document frequency. Term frequency is nothing but the number of times a particular word is appearing in a document. So was will of course have very high term frequency. Then so here document means, so let's say you have 29,800 data points, meaning these many paragraphs created by ChatGPT is what consists of your AI generated data set. Then you have 29,800 documents. Now document frequency is nothing but in how many of these documents is the word was appearing. Now imagine if the was will obviously be there in most of these documents. So the document frequency DF of this will be 29,800 itself. And inverse document frequency IDF is nothing but 1 by 29,800, right? So the IDF for the word was is very low. And there is something called TF-IDF. So TF-IDF is nothing but term frequency multiplied by IDF. So term frequency for was is very, very high, because was is appearing very frequently in all documents. But IDF is very, very low. So when you multiply TF and IDF, it will neutralize this high frequency effect of the word was. Now let's look at the other case. Some words, maybe let's say zebra. If some paragraphs are having this word, zebra will have very low term frequency, right? Because zebra is a word that will probably not be appearing in most of the documents. But now if you look at the inverse document frequency, maybe only in 2 out of 29,800 documents the word zebra is appearing. So DF document frequency for zebra is, let's say, 2, but then the IDF is 1 by the document frequency, 1 by 2. So, and this is a high number. IDF for zebra is a high number compared to IDF for the word was. So now if you multiply this IDF, this big IDF, relatively big IDF with relatively small IDF, again it neutralizes the effect. So basically TF-IDF can really very nicely capture this idea of words that are occurring too frequently simply because it's used in almost like any English sentence, versus words that are actually unique. So in our training, we noticed that if TF-IDF is not performed, transformation is not performed, the testing accuracy was low. So this TF-IDF was actually very helpful for enhancing our test accuracy. Like it was a better representation of the text data. So I just wanted to mention that. Then before coming into model training, I also want to discuss something about some custom data. So custom data is nothing but a curated new set of data that we ourselves created. We did not download this data like directly from internet. We ourselves created it. So the reason why we wanted to also create this custom data was because we could not really trust what type of data existed on internet. So we were not sure if the quality of data was good enough. So what we did is we first found human written sample data from 5 different domains. So first we found from English literature. So the passages from this book, 101 essays that will change the way you think. Then we had Master Chef recipe. Then we had tweets from 2019 or before, IMDb user review from 2018, Quora user messages regarding a certain topic. So we had data sets from these 5 different domains, which are all paragraphs, text-based paragraphs written by humans. Then what we did is we did something that we internally call as hourglass approach. So hourglass approach is like we wanted to generate corresponding AI generated versions of this data, because if we want AI versus human, AI written versus human written text, we want data from similar domains. Like if you are comparing, let's say all the AI written data is from English literature versus all human written data is from scientific literature, then obviously you don't even need to look at any other characteristics of the data. You just need to look at the, obviously the words themselves will be different in English literature versus scientific literature. Maybe scientific literature has more sciencey words, right? So I don't even know if that's the word, but basically we wanted comparable AI written versus human written data. So what we did is we asked ChatGPT to take the human written data. So we already have the human written data from this book, from tweets, IMDb reviews, etc. We asked ChatGPT to summarize it into 3 sentences. So then it will shrink the data. If there are, let's say, 20 sentences or 200 words, let's say, in the original human written article, it will be summarized into 3 or very few sentences. Then we will ask ChatGPT to, we'll make sure that after summarizing, we will erase the context of ChatGPT so that it is not aware of the original data from which this summarization was done. And then we will freshly give this 3 sentence data and ask ChatGPT to create a paragraph based on, expand it into certain number of words. So we will generate an AI written thing. So if this was originally 200 words, let's say, this might be 15 words. I'm just giving an example, okay? This is not the actual reality. Then again, so this will be human written. ChatGPT will summarize it into very small data. Then it will be again expanded back into 200 or 250 words. And this will be purely AI written. So this is how you generate data regarding the exact same context without biasing this AI data significantly by whatever was written by humans. So this AI generated data did not see 95% of what was written in this human written paragraph, because this was generated from just the summarization of the context. I hope you understand what I mean by this hourglass approach. So this we did. So, and then the models that we worked on were the following. So we used naive Bayesian, logistic regression, random forest, XGBoost, and MLP for multi-layer perceptron. It's simply a feed-forward neural network, and LSTM, long short-term memory. These were all the traditional ML models. And then we had all these hyperparameters that we varied. I don't want to go into the details of that. You're more than welcome to read the paper. And then for the advanced NLP, we used Robota Sentinel and T5 Sentinel. And this was our custom data set. And then what we did was, this is the explanation of the part where I described the hourglass approach. So basically, we asked GPT-4o Mini to please summarize this one into 3 lines, keeping the context as it is. So the big paragraph will be summarized into 3 lines. And then after removing the memory, meaning after removing the context from GPT, we will ask it to elaborate on this topic with around 600 to 750 words. So keeping the context in mind. And then this is So the reason why we did this is better than asking GPT to rephrase, because in rephrasing we are providing the entire human text data into GPT. Who knows if it is retaining certain elements of human writing even after rephrasing. So we wanted to ensure that rephrasing is actually retaining very little of the elements of human written, but the context alone is retained. So if a paragraph is about a recipe for making, let's say, some Indian dish like biryani or something like that, the human written recipe will have a certain style of writing. Then GPT will summarize it into maybe three sentences saying, this is about biryani, this is about Hyderabadi style of cooking and something else. And then again, GPT will expand just by using those three sentences, not by using the original human text. So this was the hourglass approach we followed for the custom data. And these are the results that we got for our all the models. So this includes both traditional models. These are the traditional ML models, and these two are the NLP models. And I just want to show you the accuracy. So the worst accuracy was for naive Bayesian. I mean, we expected worst accuracy to be for one of the traditional models, and highest accuracy is for advanced NLP. I don't think there are any surprises there, because we definitely did expect advanced NLP methods to have better accuracy. But what was more surprising was LSTM, logistic regression, XGBoost. These actually had pretty good accuracy, 90, 91%, 92%, etc. I personally, more than accuracy, what I am more interested in is the FNR, like false negativity rate. Basically, let's say you have written a text, right? You are a student and you wrote an assignment and you submitted this to your teacher. Now, teacher has some tool like this, and the tool is saying the painstaking essay that you were written was 98% AI written. That's not good. So I don't want false negative. Not false negative. False positives. I don't want something to be falsely detected as AI. I want something to be only. I'm okay with not detecting some AI written text for at least for the school purposes. I'm okay with not detecting AI written text. But I don't want my model to tell that something that is actually human written is to be AI written. I don't want that to happen, because that will demoralize the students. So this I want the false positivity rate to be as minimum as possible. In random forest, it's a little bit high. You can see that here. But in LSTM, it was low. In Roberta and T5 also, it was very, very low. False negativity rate, I am not that concerned. It's okay if you are missing some AI written text, if you are kind of, if it's missing your radar, that is okay. So this was about the a brief summary of our results. And I also want to show you some the results on custom dataset. So custom dataset was created because we wanted to, the open GPT text data and open web text data have certain, it may have a corpus of data which has certain characteristics, but the custom data that we created using the books, cooking recipes, IMDb dataset, etc., it was truly something that the model did not see. And you can see that because of that reason, the accuracy is actually low, much lower than what it was for the other data set. But still, you can see that Roberta advanced NLP models are really good. LSTM test accuracy is not good. Multi-layer perceptron is good. Logistic regression is again decent. So this one I really like to see, logistic regression having good test accuracy in both cases. Here also it had 90% accuracy. Here it has 84% accuracy. Then the F1 score, the false positivity rate actually is a bit high. So I personally don't like any of this. Like there is almost, the XGBoost has almost 50%, close to 50% false positive rate. So I would not use a model like this for deploying in a product. Roberta and T5 Sentinel is better, but it should be, ideally it should be even more better. So it had 0.12 and 0.16 as false positive rate. I mean, it's okay, but there is significant room for improvement, because ultimately, even if accuracy is very high, or accuracy seems to be high, you should not have high false positivity rate. Then the last thing, this was about the LIME technique, local interpretable model agnostic explanation. So this is the explainable AI technique that we used. So here we are showing the LIME plot for MLP. MLP is multi-layer perceptron, which is a traditional ML model, feed-forward neural network. And here you can see that the prediction made by the MLP model for this particular paragraph about World War II, it's saying that it's 100% AI written and 0% human written. It's having very high confidence. And you can see the kind of words that are contributing positively towards this prediction. So the words like significant is contributing towards making this AI. Words like leading is making this contributing this to be AI classified. But it's actually surprising. I like, if I did not plot this line plot, I would not have known what the model is actually looking at. And I'm also equally surprised to see this words like off negatively contributed towards making this predicted as an AI. So it's actually not making too much sense, but at least you can see that model the level of importance model is providing to each words or each tokens. Here this is from same paragraph, basically same World War II paragraph looked at by T5 Sentinel. And here you can see the words that are most used for making the prediction as AI written. So this is also T5 Sentinel also predicted this as 100% AI written and 0% human written. And these words denoted in the orange color is contributing maximum towards that prediction according to the LIME model. So I'm not sure if this is something that sheds a lot of light into exactly what the model is seeing, because LIME technique also has its own limitations. But at least when we perform the LIME technique, so what LIME basically does is it will split the entire data set into subsets. So let's say you have 10 different words in a sentence. So I'm just denoting 10 different sentences. Now, 10 different words in a sentence. Now, how do you know if this word or word number 1 or word number 2, which one is contributing maximum towards making this sentence into AI written? So let's say this word was influencing the most towards making the sentence as AI written. Then ideally, if I change this word into something else, then this entire sentence should be classified as human written, right? Very highly likely that will happen. So that is exactly what is done in LIME. So it will create subsets where it will keep this word as something random, but keep the other words as original. In another subset, it will keep maybe a collection of second word and third word, these two words as random, and remaining words as original. In another collection, it will do like maybe some other collection of words as random, and rest of the words as original. So it will create subsets where these masked, some words are masked, and those masked words are basically randomized, and remaining words are original. And like this, if you it's a slow process, by the way. Applying this will take a lot of time, but then AI can basically tell, LIME technique can basically tell which words contribute maximum, or which tokens rather contribute maximum towards predicting something as AI generated or human generated. The one interesting thing which I want to show you is the similarity between LIME plot for LSTM and LIME plot for MLP. So the same paragraph, LSTM classified as 93% likely AI generated, 7% likely human generated. And you can see that the same word significant is somehow denoted by, like in LSTM, when we implement LIME, we can see that the word significant is highlighted. Same thing applies for multi-layer perceptron. Here also the word significant is highlighted. So somehow these models, like traditional models like multi-layer perceptron and LSTM, is looking at certain other words compared to the words that advanced NLP models like T5 Sentinel is looking at. So here T5 Sentinel has not highlighted the word significant. So significant, here is it. So those are not the words T5 Sentinel is actually using to make the prediction. So this is a very interesting thing to see. And if we really want to get a trend of, are there any collection of words or a word cloud? Can we create a word cloud that most of the modern NLP techniques are using versus traditional ML models are using for predicting something as AI or human generated, I think we can do much more rigorous analysis and create a word cloud, which will be very interesting. We will probably do that in one of the follow-up papers that we are planning to publish sometime soon. But for now, this is basically what we did in the paper. We built a model, and the model is actually quite good at predicting on the data set, whether it's AI generated or human generated. The next step that we are planning is converting this into an actual product and showing, like highlighting the parts of a paragraph which are likely human generated, parts of the paragraph that are likely AI generated. Quillbot AI detector is already good at that, but we want to see if we can make something even more better, much more custom, especially for schools. So this is one of our product development goals associated with this particular research that we did. So I hope you understood or you got some idea about this paper. Please go ahead and read the paper. The code associated with the paper is also given. The link to the GitHub is given in the paper itself. At the end, I just want to show that. The code, everything is available on this particular GitHub repo. So you're more than welcome to check out the code yourself. And if you have any improvements to suggest, you're more than welcome to give that suggestion. So thank you so much. We'll again see each other in another video where we will be dissecting another paper. So thank you so much for listening, and see you again next time.